Yeah.
To give a really nice lecture on more on the coding theory side of using deep learning. So this is a new work. In the meantime, Cong has moved from a university in China. I guess you were at USTC, I think. Is that right?
Yes, that's right. Yeah.
To the University of Virginia, which is a great move for him and a great hire for UVA. And he's gotten off to a great start there with a lot of interesting work and several major NSF proposals funded, including in the competitive machine learning for wireless program. And he has a lot of interesting directions going on that I've been following and discussing with him. And so today he's going to talk about his work on federated learning over noisy channels, which will be perhaps a nice sequel for those of you who were joined our seminar last week with Denise. I should also mention a little personal anecdote. I've known Cong since he was a student, and actually tried unsuccessfully to get him as one of my very first students here at UT when I joined. He went to UCLA to work with Mike Fitz, who was a lot better known than me at that time, and joined Qualcomm after that in San Diego. Worked at Qualcomm for a number of years. So I've been in touch with Cong for nearly 20 years now, and so it's great to see you as a faculty member now at a top U.S. school, and look forward to your talk, Cong.
Okay, thanks, Jeff. Yeah, it's a great pleasure to be here to talk about some of my recent results. Actually, I think a smaller audience might even be, I think, better, because I think this work, as I haven't really said this, but this is a very recent work, and some of them may not be kind of entire. I don't think all of them are very polished, in the sense that part of it is kind of a polished work that we have the journal submitted, accepted. Some of them are very recent that we just submit the conference version, so we're still working on like journal versions of it. So definitely, I welcome comments, discussions, suggestions, and if you're interested in this, I'll also be happy to have further discussions, maybe even after the talk. So the title of the talk is Flying Under the Radar. This is actually about federated learning over noisy channels. And this work is supported partially by an NSF grant from ECCS about the wireless federated learning, and another research grant from a company called Naren, mostly about we're utilizing their resources in computation. Okay, since this is a kind of a sequel talk about following another federated learning, so maybe I don't have to spend too much time on this slide, but federated learning, or FL, is basically kind of an emerging paradigm for machine learning. More specifically, this is about distributed machine learning. And you have basically a parameter server that wants to learn a global machine learning model. Let's say, let's consider deep neural networks as an example. And the difficulty is that the server does not have data. And on the other hand, the server has access to, in some sense, massively distributed clients who have data. So the natural idea is that can we leverage basically the clients in terms of both their computation capabilities as well as their availability of data sets locally to train a global model. And this framework, I think, was presented back in over the years. And there are many attractive properties, and actually most of these properties are also challenges from which point of view. First is this the so-called non-ID local data sets. So the assumption, generally speaking, is that because the clients are not really kind of the data is not really pushed from the server to the clients. Rather, this data are generated and stored at the clients locally. So we may not have control in terms of how the data is distributed. As a result, we typically make this non-ID assumption. The other is this massiveness of the clients. In the paradigm proposed by Google, and this, I think the number they gave is maybe up to millions of kind of clients jointly train a machine learning model. And partially because of this massiveness of the clients, communication becomes really a key bottleneck, because everything now has to be communicated between the server and the clients, which are not co-located. So ultra fast, like a connection may not exist. And this leads to many follow-up problems, such as strangler problems, etc., which I'm not going to talk about today. But communication and strangler problems and basically are among the most important bottlenecks of federated learning. The last is this privacy. And this is something that I think federated learning people care about enormously, because the underlying assumption is that data set really is at the client. the hope is that the clients do not reveal any information about their raw data. This is also one of the early benefits claimed by Federated Learning, where we don't exchange data between the server and clients, rather we only exchange models. So model obviously would contain some information about the data, but it's not as bad as just exchanging the data itself. So this work is about the communication aspect of Federated Learning. And naturally, because I am myself is I'm a communication engineer by trade. So the reason I was attracted to Federated Learning in the first place was because of the communication problems. And this is one of the primary bottlenecks. People talk about this as if they are kind of a given. So when I first look at this, I asked myself, how bad is it? Why is this? So first of all, why is this communication a major bottleneck? Secondly, if it is a bottleneck, then how bad is it? So this is just one slide summarized some kind of a very simple back of the envelope calculation of this problem. So first of all, let me discuss why communication is a major bottleneck. Well, first of all, I think the reason is that we are training nowadays very extensive models. So we're not just training, a neural network with 5 kind of nodes. We're training neural networks with many, many more nodes. So because of that, you have to do a lot of communication with many parameters exchange between between clients and the server. Secondly, also the number of clients are significant, as I mentioned earlier. So you multiply these two together, you get a lot of information that you have to that you have to communicate over the upload and download links. But how bad is it? If you do a quick back of envelope calculation, just use some very well-known baselines. For example, some simple model using CNN or LSTM to train some well-known data sets, the Minister, the CFA10, the Shakespeare. These are standard Federated Learning tasks. They are benchmarks that people compare against in most of the papers. And we choose a very small, only 10 clients. We're not even talking about millions. We're talking about 10 clients. Some relatively small machine learning models. As you can see, the model itself is only like 2 megabytes or 4 megabytes, around this range. But if you do really if you just send the entire data set, let's say for minutes as an example, it takes about 45 megabytes to do a one-way communication. And once you send the data, you are done, because the server has the data, you use the data, you do your own training. But now you break this down into maybe 4.5 megabytes per client. And then you do these iterations. Because the distributed machine learning, generally speaking, converges at a slower pace than the centralized, you need multiple rounds of communications. This blows up really quickly. So if you do a quick calculation, you maintain the same kind of target model accuracy, you end up having 20 gigabytes in both links in terms of communications. So this is a significant increase. This obviously is not an optimized scenario. We're not talking, we are using a floating point representation and things like that. So this may not be, you can argue that, in reality, this will get better. But the point is that this is not even on the same order. It's several orders of magnitude higher in terms of communications than comparing to just send the data set in one shot. So I hope we agree that this is a problem. So then how do we solve this problem? How do we improve that? As I mentioned earlier, there are 2 factors here. One is that you have many communication runs. So you can reduce the number of communication runs, or you can reduce the size of the payload per communication run. Because at the end of the day, the multiplication of these 2 determines the overall communication overhead. So you can reduce one or both, one or the other or both, basically. However, when I look at this problem, and as a communication engineer, I immediately thought, this does not look like communication in some sense, right? We're not talking about physical layer. We're not talking about MAC layer. We're not talking about actual communications. We're talking about basically reducing the communication overhead. We're not talking about the communication itself. So what about actual communications? And if you look at the papers, this is mostly ignored, especially in the early, I think, the first couple of years. People don't talk about the actual communications. In recent years, researchers like myself and others from the more of a communications background started to look at this. And even with all of this, most of these papers, I think we are still making the assumption that the underlying communication tunnel is actually error-free, meaning that we assume that if you want to upload something or you want to download something in terms of the model, you can do so. There isn't really much communication error or other issues that you need to consider. And this is mostly okay, I would say, in the original federated learning setting, because I think the original setting of federated learning basically is that, for example, in Google's mind, the time scale of these communication runs are very significantly longer than what we typically handle in a wireless scenario. This is on the order of hours, if not days, for every communication run to happen. There are good reasons to argue for this. For example, you would think that clients may not want to participate, right? So they may participate only when, let's say, they are plugged into a power outlet and they do not have other tasks running on the background. So only when they are free. So because of all these other considerations, timescale is very long. So in that sense, existing protocols, it's okay, I think, to assume that the communication is error-free, using LTE, Wi-Fi cable, whatever that is. But once you get to the kind of the wireless edge scenarios, if you're talking about doing this at the wireless edge, and you introduce wireless as, this is as the same plot, but now I highlight that the medium between the server and the clients becomes wireless. This is not reliable. And in fact, you can envision scenarios where clients also have different kind of things they want to do. We have our normal data, video, audio, pure data communications happening. So federated learning is just another, in some sense, quality of service class that has to almost compete with other tasks for resources. So based on this view, we need to take into account of this wireless medium, and we need to kind of evaluate how wireless really affect federated learning. So in this talk, as I said, I will try to take wireless. More specifically, when we talk about wireless communication, we think about noisy channels. And we want to take this into account in the communication phase, where both upload and download. I like the terminology of uplink and downlink. This just makes myself feeling more comfortable in the wireless in a communication setting. But this is also called the upload and download phases of federated learning. And we want to study how federated learning is affected by this communication noise. And on top of that, once we have a good understanding of what happens to federated learning when there is communication noise, then we want to optimize communication. We want to optimize the design so that our federated learning performance can be better by having better communication designs. So this is really the first part of the talk. And if time permits, I will also talk about another probably more machine learning aspect of federated learning, where I don't talk about noisy channel or wireless aspects of this, but rather I talk about how we can actually optimize federated learning where I have device heterogeneity. This is something that's also very new, and it's different from most of the federated learning research where we talk about heterogeneity, but mostly we talk about data heterogeneity. But this is about the device heterogeneity. But again, if I have time, I will talk about this. And these are the three papers that the talk is based upon, and I'll be happy to share. Especially, I think I think the first two are already kind of published, or to be published. The second one is something was submitted last week. Or noisy channel, and this is the model that we're considering. We have this in fact is not a communication model, but rather it is a federated learning model where I explain what happens in a particular communication round. I use a notation, for example, the TEAS communication round here. I will explain in the next few slides what happens. This serves two purposes. One is to introduce to you what federated learning does in every communication round. The second is to introduce this uplink and downlink noisy channels into this framework. So the basic setting is that I have one server, but I have a total of n clients that I want to that can help me with federated learning. And in this work, we take this partial clients participating into account. So in each round, we are going to randomly select only a small subset of clients, and this subset selection varies from round to round. So over 2 consecutive communication rounds, I may have different clients participate in this federated learning process. And we also explicitly consider non-IID dataset distributions. And I didn't talk too much about existing literature, obviously, but if you look at the landscape of the literature in this general area, and every paper talks about some specific subset of the constraints. And some paper consider full client participation, but non-ID, some consider, for example, IID distribution, but partial clients, etc. And we realized later on that this is mainly because of the analytical difficulties we are encountering. So trying to incorporate all of these constraints into one analytical framework, I think that is something even machine learning folks are still working on actively nowadays. But for us, we try to do the best we can. So we try to incorporate as many federated learning unique features as we can. Okay, so the first phase, I'm going to start with the downlink phase. So the server currently has, let's say, a global model. Let's call this model a vector W. WT-1 means that this is the global model that the server has at the end of T-1's run. So the first step is for the model, global model to be downloaded into a subset of clients. Or proactively, the server may just broadcast this latest model to randomly selected client set ST with cardinality K over a noisy channel. So here we introduced a noisy channel between the server and the clients. So we assume that the received model at client K, small k, is the true global model WT-1 plus, let's say, a noise vector E sub T sup K. Okay, so obviously this, I didn't talk about the communication details here. You can think of an actual communication channel over this. You can do MIMO, you can do OFDM, you can do diversity, whatever methods that communication actually utilize, I think can be incorporated here. But at the end of the day, maybe post-processing at the receiver, you will end up having the actual model plus some noise. This noise basically is effective post-processing noise. So then you can define the SNR, which is the signal power, that is the true global model, divided by the effective noise power. And let's call this a SNR in the downlink. The sub L means that this is a downlink locally, basically, it's locally at the client. So that's why there is an L here. And T is the current time, the run, and the K is the index of the client. So this is the first phase. The second phase is a pure machine learning phase, where the local client, let's say client K, once received a global model, decoded a global model, this client runs a mini batch SGD for E epochs. So basically, the process is also very standard. We start with this received global model, and then we iterate for E runs, where every run I run a mini batch SGD, where I compute the gradient of the local loss function at the current model WT tau-1. And actually, let me use my laser pointer here. So the current model is the WT tau-1 at the client K, and I'm going to select a mini batch of data samples defined as psi tau of and K. I'm going to run an SGD computing the gradient, and then I'm going to advance the model. And then I'm going to set this as next starting point and repeat this process. And I'm going to repeat this for E epochs, and then I will have my final local model. Okay, so this is there's nothing really new here, at least from a machine learning point of view. I'm just using a very standard mini batch SGD. And after all the clients have computed their local models, and then we come to the uplink phase, where the client K will upload this latest local model, we call it XTK, to the server. This time, again, over a noisy channel. So I have uplink noise and at the client side. And here, I want to immediately emphasize that there are two choices in terms of how you're going to do the upload. The first choice, which is almost like the most intuitive choice, is you just send this latest model itself. You send this as a signal. The second choice, which is commonly used in the machine learning literature, is to say, I'm going to send only the differences of my latest local model minus the previous global model I received. So I'm only going to send the so-called model differential. And the reason is that the server already has a previous global model. So if I only need to send the differential over the uplink uplink channel, and at the receiver, the server can just add this back to the base global model from the previous round, and the server will recover the new local model from every client. And this is true if there's no noise, basically. And as we will actually see, this has very profound impact in terms of the performance. We will see this later on. But most of the talk is focused on the case one, where we just send the model itself. Again, if there's no noise, and from a pure machine learning point of view, there's no difference between these two approaches, because at the end of the day, the server recovers perfectly all the local models. But as I said, there is actually a difference. Also, I want to make a point here, where is this model differential transmission does not apply in the downlink phase. The reason is specific to the partial client participation that we assumed, which is one of the unique features. Because if you change this local clients from round to round, when another round starts, the newly selected clients may not have the previous global model as a baseline to do this model differential computation. So in that case, you will not be able to recover the latest global model by just sending the model differentials from the server. So this is, I think, is one of the important constraints, because there are existing literatures analyzing, for example, the downlink quantization and things like that. And you can think of communication actually, as I will show it later in the example. Quantization basically is a special kind of case of communication noise, right? Because quantization itself introduces noise. You can think of that as the noise of the channel. So that applies only when you have this, when you have full client participation, but not partial client participation. So here we don't actually make this case two at all for the downlink, because we assume partial clients. Okay, so lastly is this server global aggregation. So we do not make modifications here. We assume that the server just does what it does nowadays, which is, for example, the FedAvg algorithm, where we just average all the received local models from clients. So again, as I said, there are two cases here. If you just transmit the model itself, then you receive a noise version of the model, and then you do the average. You get this kind of a new global model at the server. The second case is that where you only transmit, for example, this differential, and then you rely on WK minus 1 in the server to recover. Actually, I should scratch this K, sup K here, but you just use WK minus 1 to recover this differential. You use the differential to recover basically the client model, and then you average that to get the new global model. So this is the model so far. And as I said, most of them are the same as the Federated Learning or the standard vanilla FedAvg setting. But we introduced basically two noise channels in uplink and downlink. And then for the last aggregation, we can similarly define this post-aggregation global model.
Cong, I just had a question.
Yes, go ahead.
On this model. So I mean, I guess the idea behind sending the differential is that this produces like a sparse vector that you could like compress quite a bit to send less total information. That's the point of the
that's one of, yeah. And maybe to just kind of preview a little bit of why this is also important to us. The differential actually, as you can imagine, once you get closer to convergence, the differential becomes smaller.
Right.
Right. And as a result, if you keep a constant transmit power, it means effectively you are increasing SNR. So
that was my question. Yeah. So like if you're decreasing your dynamic range or your amount of information. So I was wondering if this was a fair comparison, because you would have a much higher SNR in the case. Okay.
Exactly.
So right.
Okay, so lastly, we define this kind of a server SNR, which is post aggregation, and you would have this kind of SNR where you have the kind of the server model, the true model, the power of the true global model divided by the power of the equivalent noise at the server after aggregation. So you can make this kind of this is the model of the overall FedAvg plus the noisy uplink and noisy downlink. And the next step is to analyze this model, look at study the convergence behavior, And this first result is actually one of the main results of this talk, which is the convergence analysis of federated learning under this noisy channels, but also we are making the conventional assumptions on the federated learning framework. So we consider non-ID data set, we consider partial client participation. And these 2 points are actually, I think, points that are very unique to federated learning. So it's good to consider both of them in this analysis. The third one is that we only limit ourselves to convex loss functions. This is one thing, obviously, people can, you can say that normally if you train deep neural networks, the loss function is not convex. As a matter of fact, researchers are working on analyzing non-convex loss functions in federated learning. And this is also one thing that we are also looking at right now. But in this particular work, we will present results only for convex loss functions. And as I said earlier, we focus on the case where we directly transmit the model itself in the uplink. And I will talk about this model differential impact later on. And for the analysis, we make this kind of common assumptions that you would find in most of these papers. Loss functions are assumed to be L smooth and mu strongly convex, and the convexity is something I already mentioned. But we also need the function to be L smooth. And there are 2 assumptions on the basically on the SGD. One is this bounded variance of the mini batch SGD. So basically it says that when you do the mini batch at every round, the randomness introduced by just sampling a small subset of the data samples as opposed to the whole data set does not give you kind of a very big variance. So you are still fairly close to the true gradient. The last one is this uniformly bounded gradient. So it basically says that the gradient itself is upper bounded. Last one actually, especially I think is reasonable from a practical point of view because in reality, the computation of any gradient will be a fixed point. So it must have some kind of upper bound. So nevertheless, we are making this for commonly used assumptions. And with that, I will have this first result. This is a kind of a theorem. As you can see, it's very complicated here. But I want to highlight really what this theorem is about. So we define some parameters that's related to this mu smooth, mu strongly convex, and L smooth, and also the multiple kind of epochs that is happening in the mini batch SGD. And first of all, we notice that we set the learning rate as this, eta t as 2 divided by this. The most important thing here actually is not really what this specific format is, but rather we are having the learning rate as an O1 over T scaling. And this is kind of very, for those of you who are familiar with distributed machine learning or federated learning, this is kind of the best case scenario for convex loss function in terms of the convergence performance. We want the learning rate to scale as 1 over T. The second part is really what this main theorem is about. We are saying that we want to control both the local SNR and the global SNR. So if you recall, the sub G means the global SNR after global aggregation, and the SNR sup L of client K at time T is really the local SNR. Once you have this, once you the post-processing SNR. And we need to have these 2 SNRs control to satisfy these conditions. And the important thing here, again, is not really what this specific format is, but rather the scaling of this. If you look at these conditions, we are asking essentially the SNR at the global level and the SNR at the local level to scale roughly at basically 1 divided by T squared. Oh, sorry, I take that back. We're scaling that as OT squared, basically, for the SNR. So we are requiring the SNR to increase quadratically with the communication around T over time. Okay, so once this is satisfied, we have this convergence result, which gives us pretty much the same convergence rate plus some additional kind of a constant terms as the case where you have no noise, basically, on uplink and downlink only. So to summarize, I have one bullet point here. Basically, this is the convergence to the global optimum at a rate of 1 over T is can be accomplished if we gradually decrease the effective noise level at a rate of 1 over T squared while we keep the learning rate the same as 1/t scaling. Okay, so this is kind of a summary of this theorem, and this is also one of the kind of I think most important results of this talk. I will pause here just for a second if you have any kind of questions about this.
Hi, Cong. Just a question. I joined you relatively late, but I'm trying to catch up. For the effective noise level here, are you talking about the standard SGD noise, or is some noise specific to wireless communication? What's this effective noise?
This is the wireless communication noise. It's not the SGD noise.
Okay, so that's something controllable. Okay, so
yes.
and in your analysis, you have already considered the SGD noise, the Gibbs noise in SGD, right?
Yes, the noise of SGD is captured. And in fact, this is one of the reasons. I think we're getting ahead of ourselves, but this is why we call this flying under the radar. Essentially, the key idea, as I will talk about in a few slides, is that you want your communication noise to kind of fly under the SGD noise.
Oh, I see. I look forward to that. Thank you.
Yeah.
Hi, I have one question.
Yes, go ahead.
What do you mean by you can control the noise?
This is, I think it's more about controlling the SNR. So, for example, we cannot really control the noise that happens in the channel. But keep in mind that here, the noise is post-processing noise. So essentially, what really matters is the signal-to-noise ratio. So you can either think of the noise power to be constant all the time, and you adjust, for example, the transmit power. And this is actually one of the two examples we're going to show later on. But effectively, you are reducing the noise if you think of, for example, the power to be the constant term. But at the end of the day, it's the SNR that matters.
So, in this example, we'll have to increase the power by order t square, right?
Yes. Yeah.
Okay.
That's actually one of the first numerical examples I'm going to show.
Okay.
So what's the distribution of the noise you were typically adopt here? Is that Gaussian or?
This one, actually, that's a good point. For the analysis, we do not really make any specific assumptions about noise, but rather we have a constraint on the second. We have second order basic variance constraints on the noise.
Okay, interesting. Thanks.
Yep. Okay. So this is the flying under the radar part. In fact, we didn't know this result until actually we do the analysis itself. We're trying to derive something without knowing where the goal is. But the proof now, looking back, is really where this interesting phenomenon is revealed. So basically, as you know, we already know SGD itself is a noisy process, and with a gradually shrinking noise level, this is why you need to basically shrink the learning rate essentially. And once you start shrinking the effective noise level, and what we need to do really is that the key observation for our analysis and for this result to hold is that we want to keep the effective channel noise to not dominate the effective SGD noise. And if you look at the proof, this is where we really get kind of this control, and where this effect, once you do the convergence analysis, this term will never dominate the analysis of SGD itself. And so to make sure that my SNR control is like the previous slide, and this is how I got there actually. So details, but as I said, are much more complicated. And the additional technical difficulty here is that keep in mind that we are talking about both uplink and downlink have noise components. So these two effects, if essentially from the t minus round to t's round, you will have a kind of an aggregated effect. And you have to untangle this impact of these two noise sources separately to get to that result. And there is some additional optimization that you can do, which we haven't done yet, which is, can I maybe, for example, do a better job of uplink and do a kind of a more crappy job on the downlink and vice versa? But in this particular work, we just we focus on trying to untangle these two effects almost like equivalently. But the result is what we got in the previous theorem. But as I said, this is something probably we can further optimize. Okay, this is just a kind of philosophical explanation of what really happens in that. And again, I think the details I I don't think I can really expand that in this talk with the limited time I have. And now we're getting into the first part, which I think one of you already alluded to, is we can actually, this is a general principle, right? I want to control the effective SNR, but how do I control that? There are multiple ways you can do this. For example, we take one of the existing, federal learning design in wireless scenarios, this broadband analog aggregation, and we build on this, and then this work itself is about leveraging the natural superposition of the wireless channel, because if you have a wireless channel and in uplink, once you send something, they will naturally be superimposed with each other. So ideally, if you do this superposition at the transmitter, you should be able to get a naturally aggregated model at the receiver already. So this is the one of the key ideas of this paper, and we build upon this to further introduce transmit power control. And the derived power control is like this to uplink TPC and downlink TPC, where we need to control basically these power levels at both at the clients and the server. And when we do this, we can guarantee the conditions in the previous theorem are satisfied. And then we want to compare this against, for example, if we don't do this, if we just use, let's say, constant power all the time, or if we only do the the per round TPC, as in this paper, where we only, in the uplink, we only do the channel inversion. The channel inversion here is really to make sure that at the receiver, I get an equal, evenly, aggregated models from every client, because different client sees different channels. So I can use channel inversion to get rid of this kind of heterogeneity in the channel conditions, so that I get a summation of this model W at the base station. And on top of that, we are introducing the transmit power control, which is more over time. This transmit power control, because it scales over T. So we're still doing the channel inversion per communication round, but on top of that, we're doing across communication rounds power control to scale up the power. And naturally, in order for us to do a fair comparison, we're going to insist on, for example, the total energy spent over, let's say, T communication rounds are the same for both constant power and for example, the transmit power control here. Okay, so this is the first example we're trying to show, and I'm comparing three baselines. The first is the natural performance bound, which is noise-free. So just in the ideal case of federal learning, we assume there is no noise in either uplink or downlink. So this is a performance upper bound that we can hope for, basically. The second is this equal power. As I said, every communication round uses the same transmit power, but you can still do channel inversion based on the channel conditions. The last is this OT square increased power, and this is our new method. And we normalize the transmit power, total energy, actually, and it shouldn't be called the power, total energy over T rounds. And we do this over two standard data sets, MINUS and the CFAT10. We do actually both IID and non-IID, and we do partial clients. Okay. So the results are summarized in this table, and let's look at this basically two big columns one by one. The MINUS result, really, if you look at this, let's look at IID. The accuracy that you get at the end of T's round very much is there's for a simple task, there isn't really much to really screw up the convergence in some sense. And we don't really see much difference, although we do see a slight improvement, but generally speaking, I think it's not significant enough to really claim that there are advantages here. But with a little bit harder task of the CFAR10 classification, the gain becomes noticeable. If you look at the baseline, which is noise-free, we have this 79% accuracy, and the increased power actually gets you fairly close. Actually, if you normalize the baseline as 100%, the increased power approach gives you 99.16% for the IID case. And the equal power, which is the one that you are having basically same constant power, same power for every round, really is not doing as well as we did here. In fact, we observe something interesting from the simulations where the training loss actually would increase if you do the equal power under certain configurations. This tells me actually if you do not handle the noise at all, because the constant power case would correspond to you don't handle the noise, you just transmit, and the receiver, you just do the aggregation without considering what the noise really is. If you don't handle that, keeping that in mind, that the convergence at the later phase is more kind of sensitive to the noise, then what happens is that towards convergence, you would actually see performance degradations. We've seen this kind of curve in certain configurations, that you have the convergence, the accuracy increases initially, but actually it drops at the end. Okay, so a second example, and as I said, the general principle of having this kind of a SNR control applies to different applications. You can think of transmit power control. Another example is that I'm going to do quantization, right? And I can consider error-free channel, but I do quantization at the clients, and I do quantization at the base stations. Then in that case, the quantization itself can be thought of as introducing noise to the received model. And this same
sorry, here the quantization happens after you have already do the full precision computation of the gradient. You didn't do quantize the training, right? You just first compute the full precision and then quantize.
That's correct, because here the quantization, the purpose of quantization actually is not for example, storage or computation purposes. It's the quantization here is meant to help
increase
communication.
SGD noise. Yeah.
Okay. Yeah. So here it's actually we do quantization because at the end of the day, let's say you have a weight of 1.2475. Now you have to transmit this weight number from the base station to the client, or from the client to the base station. In communications, you always have to, you do digital, communications, so you have to convert this into a sequence of bits. This is where the quantization also happens, because you have to do communications. Now you have to do bit ones and zeros. That naturally also involves a quantization procedure. But again, this is different. Yeah, as you said, this is different from the typical quantization that machine learning people do.
Okay, thanks.
Yeah. So as I said, so if you have, let's say, a 1.35, and then you quantize that into, let's say, 3 bits for communication, then that also introduces noise. So similarly, the result would apply here. But the interesting thing, the result is that now the number of bits, if you apply the same SNR requirement, it translates to scaling up the quantization bits as log t over time. So you need to basically increase the number of quantization levels. And this, again, if you think about it, is not, in some sense, not that surprising, because as I said, the later phases of these federated learning typically are more sensitive because the models are, the SGDs are more important in terms of averaging to get to the final and the model. So the noise there, you'd want to keep that noise to be small. That's why you would increase the number of bits intuitively. This makes sense. But what this theorem actually says is that you need to increase at the log t scaling to get to this to make sure that the quantization noise does not again dominate your error. So we did a little bit of also simulations here. This is basically again the dark red line is really you have the floating point, so everything is perfect. You transmit the model itself without any quantization, and then you do, for example, a 2-bit quantization throughout the time. Almost 1, 2, 3. You can think of this as, maybe 1/3 of the time you have a 1-bit quantization, the middle third you have a 2-bit quantization, the last third you have a 3-bit quantization, roughly speaking. But as I said, this scales actually in the logarithmic fashion. So there are some kind of further kind of rounding you have to do, because a log t is not always going to give you an integer number. So you have to do some rounding somewhere. But nevertheless, we make sure that the total number of bits, let's say in this case, throughout 600 rounds, are the same for all. Actually, the new method is the same as a 2-bit, because the average is 2 bits per computing round. Then you see this kind of interesting kind of a stair kind of a behavior, because initially you have 1 bit, it does not start very well, but once you increase a bit, it catches up really quickly, and at the end you kind of jump over the 2-bit baseline, getting to a better point. And the same actually.
Hi, sorry.
Yes, go ahead.
Sorry. You just mentioned that you control the bit budget across the whole 600 training or communication rounds. So
Right.
I'm not sure how you did that. So for example, if I use a lower bit, do you transfer? So from my understanding, then if you transfer this gradient and you use less bits, then the communication budget costed at this round is reduced. So how
Yes.
you can how you make all those curves share the same total budget, right? So do you communication more rounds like originally every iteration, every 2 iteration, now you can do more frequently than that?
So no, so this is a fair comparison in the sense of the total number of bits that are transmitted. Let's say let's say from the client to the server. So over 600 rounds, let's say every parameter in the blue curve, a total of basically 1200 bits are transmitted. And the same goes for this again the 1, 2, 3 bit allocation curve. So overall, at the end of 600 rounds, I have 1200 bits transmitted from the client to the server for this particular weight.
So wait, but you are saying that all those 4 curves here cost the same total number of bits transmitted in this whole communication process. I'm right here, right?
Yes.
Okay, then comparing 2 curves, like for the bit equal 2 and bit equal 3 curves. So from my very naive layman's understanding, if you use less bits, like the blue curve, should it every time it should cost less bits when it transmit, right?
Yes. So 2 and 3 are not a fair comparison. Yes, that's correct. So
the fair comparison is not across the curves. Okay.
Right, it's not across. It's actually the 3 curve is more like a natural upper bound, because at the end of the day, my algorithm only goes up to 3 at the end. So we shouldn't expect that to be better than 3, because the bit 3 curve is using 3 bits all the time. And in my in this 1, 2, 3, I only use 3 at the end. So obviously I wouldn't be able to kind of beat that. But I want to see how much gap I have. The only fair comparison in this case is actually the blue line and this 1, 2, 3 bits allocation line. This is a fair comparison. The others are not.
That's very interesting. I'm just being curious. So are you sure this effect is because of communication noise, or is it because the training itself could be done in low quantized bit regions? For example, from what we know from our own experiments, if you train a network on the full precision bit, you reach certain accuracy. But if you first train the quantized network on the really low bit regions, even 4 bit, 8 bit, and then fine tuning it on full precision regions, it can still reach almost the same high accuracy. So even without introducing the communication noise, the bit itself, so I guess the short message here is the larger SGD noise effect in the early phase of training, because of its convex-like nature, could be undone in the later stage of SGD training. I think that would account some. That may lead to some similar phenomena here too, but I'm not sure because I'm totally uneducated on the wireless side. Sorry.
No, this I'll be happy to actually discuss this in more, because we didn't really do anything on the machine learning side with regarding the quantization itself. This one is the quantization only happens when you already train the model, which is a floating point model. And then only one, for example, in the left curve, only when you try to send this local model to the server.
But this is equivalent.
Yeah.
Hello?
Sorry, go ahead.
Oh yeah, sorry.
Yes,
So I just experienced some broken lines. Sorry. So, but this could be if I only have if I just treat one device here, there is no federated learning, just one device. Yep. Then your training is reduced to having full precision weights, full precision activation, quantize the gradient, but with full precision latent weights, right?
Yes.
Yeah. So in this case, in this case, in this reduced case, I'm pretty sure you can still have similar curves like this. I mean, if you start with 1 precision gradient, then 2 precision gradient, 3 precision gradient,
right.
you can, yeah, it will be very similar. I would bet it would still look very much like this yellow curve versus the purple curve. So my real question is, I'm not sure whether this is because of the communication noise or the SGD redundancy itself.
Yeah, in this particular case, I agree. This particular case, in fact, it does not have any communication noise. The noise here is really the quantization noise. So I haven't even introduced a communication noise here. So this is basically just, yeah, just because I scale up the bits, so naturally my quantization noise reduces, right? So this is just another example showing that I can do an effective SNR control, right? Because if I have more bits, naturally my SNR improves, right? For the quantization, the SNR improves. So this is actually just showing that, yeah. I don't have the actual communication noise in this particular example.
I got your point. That makes sense. Thank you.
Okay. All right. So let's see. Okay, I promised I would talk about the weight differentials. In fact, this is very interesting. Back to Jeff's earlier question. This result actually, if you consider uplink weight differential, as it turned out, the analysis tells us we don't need this OT square uplink SNR scaling. In fact, our theorem states that in the uplink, you can use a constant SNR. And you're still going to be able to achieve this 1/t convergence rate. The reason, as I already mentioned earlier, because the model differential shrinks basically dynamic range over time. So if you keep the constant SNR, you are basically using the same power, but you are using the same power to transmit a much, much smaller basic value over time. So effectively, you are increasing, in some sense, your SNR because you are using some power to transmit 1 versus you are transmitting 0.0001, and the same power would give you kind of a better improvement in terms of the SNR, right? So this effect, the weight differential itself, actually in some way handles this SNR, effective SNR requirement. As a result, we don't have to control the SNR at all. So this is a very kind of interesting observation, I would say, at least to me, because people talk about, as I said earlier, people don't really differentiate weight transmission and weight differential in machine learning. But once you have the noise, be it the channel noise or the quantization noise, doing these two different things actually have a significant difference. And this actually alludes to my first part of the conclusion. I don't think I'll probably have time for the second part, but let me conclude the first one. This is something that I think I also want to emphasize. There is probably a bigger fish to fry here. But in this work, we have discussed how uplink and downlink channel noise affect the federated learning performance. As I said, the key idea is to fly under the radar, to control the effective SNR or the effective channel noise such that it is buried below the noise of SGD. But the bigger fish I mentioned is this. We have noticed a much more general principle, and this is something we call resource rationing that emerged from this study. The philosophy is this. We notice that federated learning obviously is not the same communication task we typically handle for communication engineers. For example, we handle video, we handle image, we handle internet data, we handle all this we handle voice. But most of our communication systems are designed so that we only consider almost like an IID source. If it's not IID source, we do source coding, we get to IID source. But federated learning, this is a long-term process. Every round, you can say that the gradient matters, but you can also say the gradient does not matter that much because if I lose something, I may be able to get it back later on. So this is a long-term process consisting of many progressive learning rounds, which would collectively determine the final outcome. So you care about the final outcome, but this final outcome is not just determined by one kind of communication. So the learning rounds, as we have seen from machine learning, have varying significance towards the final outcome. So given that in a wireless edge communication scenario, in the edge learning scenario, training a neural network for federated learning is not probably the only thing that you want to do. You are competing against other tasks. So if you have, let's say, a bigger kind of a broader resource constraint that you can allocate maybe between federated learning and some other tasks, then the resource rationing basically is the principle that says later is better, meaning that, okay, if I have to allocate resources among federated learning and a bunch of other things, I can give federated learning a little bit of very limited resources at the beginning, And I know from this the result that this would affect federated learning initially, but if I, as a compensation, if I save these resources and I ration the resource so that later on I have sufficient resource for the later stages, I will end up having a much better learning performance than, let's say, giving a constant resource all the time to federated learning. So this is really the, I think as I said, the bigger maybe principle here. I do not have time to talk about this other work, but I'll be happy to maybe send the slide and the paper after the talk. So feel free to email me any questions you have. By the way, this second paper is something I'm also going to talk about in, I think in a week. There's a workshop on edge learning, and this is the talk of that workshop. With that, I will stop here, and I'm happy to take questions.